Hello, welcome to Virtual VCF West. I'm Len Shustek, co-founder of the Computer History Museum, and for 25 years was chairman of the board, but I've recently retired and I am now chairman emeritus, which gives me time to work on other fun projects like the one I'm going to be talking about today. This is about magnetic tape data recovery in software. The museum has thousands of mag tapes, which we'd like to read, and we don't often have the equipment to read them. But my motivation for starting this project was actually much more personal than that. When I was an undergraduate at the Polytechnic Institute of Brooklyn in the late 1960s, I worked on a project to write a PL1 subset compiler called Plago. And it was the project that made me want to transition from being a physics major to being a computer science major. When I left Poly, I took a mag tape with all of the source code on it and kept it with me all of those years. And for 50 years, it's been in the attic. And never having been read and not stored under environmentally friendly conditions, I was suspicious that it was going to be difficult to recover the data. And in fact, it was. I dropped $1,000 on a professional data recovery company who promised to do their best job to recover the bits, and they basically failed. The red question marks on this printout below shows all of the places where there were errors. There were hundreds or thousands of errors in every file, which led me to wonder, is there a better way to try to recover the data than using standard tape drives? The standard tape drive uses a lot of hardware. It starts with the read head, and then there's a preamp and maybe a differential amp and a differentiator and a comparator and a threshold detector and a zero crossing detector and a data bit decoder. And that's just to extract the bits. And then you have to do the block handling and the word assembly and the error handling and all of that. And if anything goes wrong, there's not a lot of knobs you can tweak to make the decoding better. There is a better way, or a different way, and that is software-based. Now, I was inspired by a project I knew that Paul Pierce up in Oregon had done in 2004 with some Java software to do software-based data recovery. You start with the read head, you do the minimal amount of hardware necessary to boost the signal, do an analog to digital conversion, and then do all of the subsequent processing in software. Detect flux transitions, use that to determine the bits, assemble those bits into words and blocks, determine your success, and then try it again if it's not good. And you can tweak all of the parameters for those algorithms so that you can do it over and over again based on the recorded data without ever having to read the tape more than once. That's important because for some of these old tapes, sometimes one read is all you get, and the process of reading it strips the oxide off the tape and you've lost the opportunity to do it again. So I thought this was a good idea. My first attempt was to build some hardware to do the analog to digital conversion. I found this great chip from a UK company called Wolfson that was subsequently bought by Cirrus Logic. And I put together a prototype board using this chip that does 9 parallel analog to digital conversions at one time. They designed it for CCD recorders. I was very frustrated. That chip has about 400 configurable parameters. I was never able to configure them correctly so that it would work. The engineers at Cirrus Logic were unresponsive, and I basically put the project aside. And then there was a brilliant insight from, I think it was Al Casso, who said, don't build your own hardware. Take a standard tape drive with a standard read head and the standard preamp, and then use a A to D logic analyzer to record the analog signal and digitize it before all of the rest of the electronics in the tape drive. And that's what we did. We took a Qualstar 1052 tape deck, wired in a Soleil 16-channel logic analyzer. I'm a big fan of Soleil, by the way. They make fantastic products. And the result is a series of waveforms that look like this. And we can collect anywhere from 6 to 16 tracks. 100 to 10,000 bits per inch. The height of the peaks here, by the way, are irrelevant. This is a particular kind of tape encoding where the only thing that matters is the distance between the peaks, not the height of the peaks. So what data do we want? Well, we'd like to get about 20 to 30 samples per bit to give our software algorithms the maximum amount of flexibility. If you're running the tape past the head at 50 inches per second, and it's an 800 BPI tape, and you want 20 samples per bit, that works out to about 800,000 samples per second. That's loafing along for the Soleil analyzer, so no problem at all reading that data. You've got to move the tape past the head at a reasonable rate. Remember Faraday's law, where the voltage is proportional to the flux change per second. So you need to move it pretty quickly. It produces lots of data, but the Soleil analyzer actually uses the computer's virtual memory as its storage. So it's essentially unlimited. What it produces for us is basically a spreadsheet, a CSV, comma-separated value text file that contains a timestamp and the voltage level on each of the heads at the time you take the sample. These files can be huge. For several minutes of data, they could be over 50 gigabytes. What we did, and I worked with Al Casso on this as well, is to define a compressed format for the data so that we could more easily process them and store them. It uses 16-bit scaled integers with self-describing headers, and I wrote a utility program that converts to and from the spreadsheet format to this compressed format. The result is about a 10-to-1 space compression, and it's processed about 2 times faster. Well, then you've got to process all the data. So I did what I love to do, which is write lots of C. It's at this point about 7,000 lines of C code. It's all up on my GitHub repository with the address at the bottom of the screen. So if you're interested in looking at it or using it, feel free to take a look at that. It's the kind of code I love to write. There's no graphical user interface. It's a command line interface with lots and lots of parameters to control the decoding. One of the things it does is allow you to specify a set of parameters to decode each block. And if the decoding is not correct, it can choose an alternate set of parameters. And it can try parameter blocks over and over again until it gets the best possible decoding. This is an example of a set of parameter blocks for phase encoded waveforms, where you get to control the clocking windows and decay times and the peak detection parameters and pulse adjustment, because pulses tend to move depending on the sequence of bits and so forth. Lots of parameters that are dependent on the kind of bits that we're decoding. So the overall data flow is the Soleil logic analyzer produces a CSV file. We convert that to our compressed binary format called tbin, and then decode. And the result of the decoding is, for one thing, a binary file that contains the raw data we've decoded. We also create a .tap format, which is Bob Subnick's SimH simulator format for tapes that can drive simulators for a variety of machines. A log file that tells us how the decoding went and what problems were discovered. A text file where we can decode the binary data into interpretable text based on a number of different decoding formats, ASCII and BCD and all of the rest. And then we create our own CSV file, spreadsheet file for debugging information. And here's an example of the debugging information. It's a reconstruction of the analog signals we saw, here with the little bips showing where we detected peaks and valleys in the data, and some information about how we reconstructed the data flow. This can be very handy when you come up with a tape that has a difficult to decode set of bits. So there are several things we have to do. First is obviously detect the transitions, the flux transitions on the tape. There are 2 options for doing that. One is a moving window peak detector that looks for the peaks of the the signal. You can specify the width and the required peak rise. And depending on where you're tapping into the electronics of the tape drive, you may prefer to look at the differentiated version of that and look at zero crossing rather than peaks. And there you can specify things like the height of the peak before it becomes considered to be a valid data bit. So once you've detected the peaks, you need to create the bits, and there are lots of different ways to do that. One of the earliest ones is NRZI, non-return to zero inverted, where a 1-bit is a transition in the middle of a hypothetical bit period, and a 0-bit is no transition in that bit period. This was used for almost all 7-track tapes, for 800 BPI 9-track tapes, for Whirlwind tapes. One of its problems is that it's not self-clocking. Notice that if there's a continuous series of 0 bits, there are no transitions. So either you have to be perfectly aligned with the bit clock as it was originally written, which of course is impossible, or you have to somehow otherwise reconstruct the clock. And the traditional way of doing that is requiring that the bits have odd, that the characters on the tape have odd parity, so that you're guaranteed that at least 1 bit has a single bit transition in the middle of the bit period, and you can use that to realign your bit clock. A way to solve that problem is to use phase encoding. This is what was used for 9-track 1600 BPI drives, which is self-clocking. There's a bit transition for every bit. In one direction for a 0-bit or another direction for a 1-bit. And then there's a transition at the bit boundary as needed to prepare for the appropriate bit transition at the middle of the bit. All of these formats are different. They all have different kinds of error correction. They have different conventions for file marks. For example, in phase encoding, file mark, which is a non-data block that represents the division between sections of the tape, is a whole bunch of flux reversals on tape 2, 5, and 8 only, and silence on all the rest of the tapes. These are completely arbitrary definitions, and decoding for these are all built into the program. The most complicated format we've done is group-coded recording, GCR, which was kind of the last gasp of 9-track half-inch tape drives that generated 6250 BPI data bits per inch based on actually 9,042 bits per inch of data stored on the tape. They used NRZI, but they encoded every 4 bits into 5 bits on the tape to guarantee that there are periodic 1-bit transitions so you could do clock recovery. Incredibly complicated, lots of fun to write the code to decode that. There are several other problems we have to deal with. One is head skew. When the tape was either read or written, the tape might not have been perfectly perpendicular to the movement of the tape, which means that bits come in at different times depending on which track they're in. This is an example of a tape with a 200 microsecond nominal transition between bits, but the bits can be as early as 183 microseconds and as late as 250 microseconds. That creates havoc with the decoding, especially for the non-self-clocking formats. So one of the things I do is to pre-read 1,000 transitions on the tape. I determine what the head skew is, and then insert delays in the early arriving tracks so that all of the track data arrives at the decoder at the same time. So this is before the deskewing, and this is after the deskewing. Another problem to deal with is amplitude changes. As the tape is read, or maybe as it was written, the amplitude varies, and if you're doing especially peak detection, that can cause a problem. So we implement automatic gain control that's either based on average of the last few peaks or an exponential weighted average of the previous peaks. And again, these are things that you can control in the parameter sets that you provide to the program. Speed changes are another thing that needs to be done because either when read or when written, the bit rate can vary from nominal. So as we see the bits coming in, we update the speed based on the recent history. Again, based on average spacing of the last few bits or an exponential weighted spacing. Once you've got a good fix on the bits, you can try to produce, correct errors. There are several ways of doing that. One is you can deduce the bits that might be bad from parity. You can correct the bits if the format has error correcting codes or longitudinal check words. A surprisingly good technique that seems to work often is to fake during a dropout on the tape that the bits you are missing were the same bits as before. There are a surprising number of 0 bits on lots of these tapes. So this is an example of a tape that we were successfully able to recover the data from, even though there are some serious dropouts in various of tracks. So how does it do? Well, I'm happy to report that on my Plago tape, 100% of all the files were recovered. And I was able to read the 360 assembly language code that I wrote 50 years ago, and of course don't recognize a bit of. As you know, the half-life for remembering what code you've written is about 6 months, and after 50 years, you remember none of it. But it was successful, and we have since applied that to many other tapes in the Computer Museum's collection. We have lots of tapes from Doug Engelbart's NLS project over at SRI, other tapes from the SRI PDP-10, Microdata Reality Operating System, Lawrence Berkeley Lab tapes, Project Genie at UC Berkeley, tapes from BBNN, and so forth. We've made a good start at decoding the tapes in the archive of the museum, but there are lots more to be done. At a higher level, why are we doing this? For me, it was mostly nostalgia to look at the code I'd written 50 years ago. But there are more important reasons as well. We can really use this to recover lost knowledge about early computers and early software and operating systems and application programs. These are techniques that you can use for all sorts of digital archaeology of trying to understand from our digital past what was done in the early days. It also provides authentic programs written in the day for restorations and simulations so that we can have a better idea of the simulated machines and what they were used for. Here's an example. Whirlwind. Whirlwind was in some ways the machine that inspired the creation of the Computer History Museum, or actually its predecessor organization, the Computer Museum in Boston. Gordon Bell had written a book with Alan Newell called Computer Structures, where he talked about many of the pioneer computers, and one of them was Whirlwind. And when he got wind of the fact that MIT was basically throwing out Whirlwind, he went to the Smithsonian and said, "You've got to preserve this. This is an international treasure." And the Smithsonian said, "Thanks, but no thanks. We don't collect computers." Well, that was Gordon's inspiration for starting the Computer Museum in Boston, which in the late 1990s became the Computer History Museum here in Mountain View. Well, along with Whirlwind, which we now have in Mountain View, or at least large parts of it, there were about 150 tapes, mag tapes, that had been created on that machine, 6-track tapes, none of which had been read since the machine was in use. So we decided to try to apply this software-based decoding technique to the Whirlwind tapes. Now, these were 6-track tapes, and we don't have 6-track heads. Al Caso, I think again it was, who had the brilliant suggestion of not bothering to try to create or find a 6-track tape, but just read it on a standard 9-track tape. If you look at the geometry, the 6-track tape tracks are 50 mils wide. If you map those to the closest 9-track head and a standard drive, it's only about 14 mils apart. And guess what? You get perfectly adequate signals. Yes, the 3 heads that are in between tracks produce junk, but that doesn't matter. The 6 tracks that are important produce perfectly readable data. And then we need to read the data. Whirlwind is basically a NRSI format. It has no parity or other checks, but each track is duplicated 2 times, and there's a clock track, which is also duplicated. So for each character on the tape, only 2 bits of data is encoded, which allows us to recover from a lot of the dropouts and errors that we knew we would be finding on the tape. It, of course, has its own bizarre format for a tape mark. In this case, it is transitions on both copies of the least significant bit and no transitions on any of the other tracks. So armed with this decoding that we put into the software, we started a dataflow, which had Al Caso reading the tapes using the Qualstar tape drive and the Soleil logic analyzer to produce the waves, basically the analog information in digital format. I converted those waves into bits and then data blocks. And then Guy Fedorko took that data and is converting it into programs and data information to drive his simulator of the Whirlwind. The results so far that we have decoded about half the inventory, about 81 tapes, 162,000 data blocks, only 0.13% of them had errors that we were not able to recover. So we've recovered about 10 megabytes of original Whirlwind data. There is both data and source code in there. I was hoping to see text, early email, some kinds of, the beginnings of the great American novel. But unfortunately, there is a little bit of text, but very little. As Guy points out, the data was so limited that people would not waste it on storing text. But it's been a successful project. It's been lots of fun. This is actually a lead up to Guy talking about what he did with those recovered data in driving his simulator of the Whirlwind. And I hope you stay tuned for his talk as well. It's a little bit unsatisfying doing this without any mechanism for feedback. So if you have questions, feel free to email me. And I hope perhaps next year we'll have an opportunity to do this in person. Thank you.